Hi dear students, this is M.Zahir Ahmed, lecturer in physics from Osmania College, Kurnool. The topic of this session is transistor configurations and their characteristics. Today we are going to discuss about what are transistor configurations, different transistor configurations and how their VI characteristics can be studied. Now, let us review about fundamental operations of the transistors. First, we will study about physical structure and operation. After that, we will go for configurations of transistors, namely common base configuration, common emitter configuration and common collector configuration. Now, first let us have a review about physical structure and operation of the transistors. Now, physical structure of BJT, bipolar junction transistor. Now, both electrons and holes participate in the conduction process of bipolar devices. That is why it is called bipolar device. Here, unlike metals, in metals we are having only one type of charge carriers, namely electrons, whereas in BJT, that is semiconductor devices, we are having two types of charge carriers, namely electrons and holes. Now, BJT consists of two PN junction diodes back to back connected in a special way. Now, the first diode, PN junction diode consists of emitter and base junction, and the second diode consists of collector and base junction. The transistor is a 3-terminal device. We bring 3 terminals from these 3 regions, namely emitter, base and collector. Now, the transistors can be PNP type or NPN type, depending upon a P type is sandwiched between 2 N types, or an N type is sandwiched between 2 P type semiconductor materials. Now, in the normal course of operation, what we do is we connect a forward bias at the emitter base junction and reverse bias at the collector base junction. Now, you can see here at this is PNP transistor. In this PNP transistor, this is emitter and this is base. Now, between this emitter and base, we have connected positive polarity. Emitter has been connected to positive terminal of the battery and N type base has been connected to negative terminal of the battery. Now, it gets forward biased. When it gets forward biased, this holes will get swept from emitter into base region. Now, base region is deliberately made smaller in size. Now, as soon as the holes enter into the base region, recombination process starts. Holes and electrons get recombination, but as soon as the holes enter into the base region, which is N type, and these holes are minority charge carriers in this N region, this reverse bias that has been applied across collector and base junction will sweep these holes towards collector region. Now, during the short stay period during which recombination takes place, some of the holes are lost in the base region. Now, the transistor is considered to be good if less number of recombinations take place in the base region. Say for example, if 100 holes have entered from emitter region into base region, if only 5 gets recombined, remaining 95 will be transferred to collector region. So, that the total number of holes that have been emitted are 100 and transmitted are 95. So, this is considered to be a good transistor. Now, in some cases almost 99 holes are transmitted towards collector. Now, this is the best transistor. Now, this will determine its efficiency. Now, next going to the PNP transistor working. Now, in this PNP transistor working, we connect the circuit like this one. Now, here we are having a base resistance and emitter resistance. Now, when forward bias is connected to this emitter base junction, small base current will be flowing into the terminal. Now, this will cause recombination to take place in the base region, and 95 holes or 99 holes are swept into the collector region. Now, this accounts for collector current. Now, the ratio emitter collector current, the ratio between collector current and emitter current is called current transmission ratio or current gain of this particular configuration. Now, let us go to different modes of operation. Now, the transistors can be operated in different modes depending upon what type of bias we have applied at the junctions. Say for example, in this table we have seen that the transistors can be operated in cutoff mode, active mode and saturation mode. Now, in the case of cutoff mode, both the emitter base junction and collector base junction are reverse biased, whereas in the case of active region, emitter base junction is forward biased, whereas collector base junction is reverse biased. Now, in the case of saturation mode, both the junctions are forward biased. Now, cutoff mode and saturation mode are applied in switching modes, switching circuits, whereas for amplification purpose we make use of active mode. Now, let us take configurations of a transistor, that is our prime topic now. Now, we are discussing about PNP, wherever possible we will discuss NPN also. If PNP is discussed, then NPN is almost analogous, or if NPN is discussed, PNP is almost analogous. Now, let us take now generally the transistor is used as an amplifier and it has three terminals, namely emitter, base and collector. Now, for transistor to be used as an amplifier, we need to have two ports, one input port and the other output port. At the input port we should have two terminals and the output port we should have two terminals. But since the transistor is only 3 terminal device, we need to make one of the terminals common to both input as well as output. Now, if the common terminal is base terminal, then it is called common base configuration. Now, in common base configuration, no current gain takes place, but only voltage gain takes place. Now, next comes common collector configuration. Now, in common collector configuration, collector terminal is made common to both input as well as output. Now, here current gain takes place, but no voltage gain takes place. Now, in the case of common emitter configuration, we make emitter terminal common to both input as well as output. Here both current gain and voltage gain takes place. Now, let us first take common base configuration. Now, we will see how it works and what are its VI characteristics. Now, see here we have given an NPN transistor and NPN transistor structure and circuit symbol. Now, here in this mode, that is common base mode, we are having two variables at the input and two variables at the output. Those two variables are input current and input voltage, and at the output we are having two variables, namely output current and output voltage. Now, at the input we are having emitter current and emitter to base voltage as two variables. At the output we are having collector voltage and collector current as the two different variables. Now, this is an experimental arrangement in order to get the VI characteristics of the transistor, that is PNP transistor in common base mode. Now, you just see that we have supplied two power supplies, namely VEE and VCC. VEE is called emitter supply voltage and VCC is called collector supply voltage. Now, here with the help of two pot meters we can vary the voltages that have been connected to emitter or collector terminals, right. Now, we are having 1 voltmeter in order to measure the voltage between emitter and base. Now, here since it is a common base configuration, all the voltages are measured with respect to only base terminal. Now, here the input variables are emitter current and emitter voltage with respect to base, and the output variables are collector current and collector voltage. Now, this circuit will come again next time. Now, this is the input characteristics. Input characteristic is a plot between input voltage and input current. Now, here we plot a graph between input voltage and input current. Now, here in this particular graph we make the output quantity, namely V collected to base voltage constant. Now, let us see that first we have connected 1 volt supply at the collector and we will maintain it constant. Now, when we maintain it constant and we vary emitter to base voltage and note down corresponding emitter current, you can see that it is essentially that of the characteristics are that of a PN junction diode. Now, you can be in a position to see that here this particular curve will depict the VI characteristics of the common base configuration when collector to base voltage has been fixed at 1 volt. Now, in the next case for the next curve we fix the collector to base voltage another value, say in this particular case it is 10 volts. Now, again you can see that it is essentially that of a PN junction diode. The curve is exactly that of a PN junction diode. And finally, we are having a curve for VCB equal to 20 volts. Now, you can just see that the curve is shifting towards left. It indicates that when we increase the collector to base voltage, then the holes that have been injected into the base region are swept more quickly due to this high collector to base voltage, like this one. Now, let us coming to the output characteristics. Now, here the output characteristics are a plot between output voltage and output current for different values of a fixed input current. Now, here you can just see that on the x axis we are taking collector to base voltage and on the y axis we are taking collector current. Now, here we are having 3 different regions, namely cutoff region, saturation region and active region. Now, here we just see that when base current has been made 0, then no emitter current flows and simultaneously no collector current will be flowing. Now, the transistor is said to be in the cutoff state. Why? Because when we do not provide any emitter current, then the holes cannot be injected into the base region and those holes cannot be swept to collector region and the transistor is almost cut off. Now, the region shaded region at the x axis depicts cutoff state. Now, after that we just see when we fix emitter current to about 1 milliampere, we can see that the curve has moved up, indicating that the collector current has started flowing. Now, we just see that in the active region, though we are varying the collector voltage, but no significant collector current variation takes place. Yes, that means the output current depends only upon the input current, but not on the collector to base output voltage. Now, if we keep increasing the emitter current, then we can see that the curve is shifting upwards. Now, this entire region is called active region. In the active region, the collector to base junction is perfectly reverse biased and emitter to base junction is perfectly forward biased. Now, coming to this another shaded region to the left of the y axis, it is saturation region. Now, saturation region is where we are not applying sufficient reverse bias to the collector junction. Now, here you can see that though we are increasing collector to base voltage, the collector current is also increasing. We just see that, which is not desirable. This will happen only in the case of saturation. Now, after a few tenths of a volts, the collector current almost becomes independent of this collector voltage, like this one. This is output characteristics of the transistor in the common base configuration. Now, before going to common emitter configuration, let us know something about the Darley effect. Now, in the previous case we have seen that though we are varying the collector to base voltage, but no sufficient collector current increase is taking place. But in the case of common emitter configuration, if we increase the output voltage, then output current increases. This is due to Early effect. What is this early effect? I would like to explain now. Now, here you just see that we are having a transistor, emitter, base and a collector. For the sake of clarity, they have been shown as having equal dimension, but in fact the base region is very small. Now, we know that at the two junctions we will be having a depletion layer. Now, whenever junctions are formed, then what happens, holes and electrons will combine crossing the junction, and a depletion layer is formed, and the depletion around the depletion layer will be having barrier potential. Now, the same thing happens at the collector junction also, but when we apply forward bias, this depletion layer reduces, and if we apply reverse bias, the depletion layer extends. Now, since we are applying forward bias at the emitter junction, the depletion layer at the emitter junction reduces, whereas we are applying reverse bias at the collector junction. So, when we apply reverse bias at the collector junction, what happens is this depletion layer extends. Now, it will be extending less in the collector region and more in the base region, due to the fact that base is very thinly doped. Base is very thinly doped. For that reason, what happens is the effective width of the base decreases. When effective width of the base decreases, what happens is the time of stay of injected carriers that have been injected from emitter into base will reduce, and less recombination takes place. Say for example, earlier 100 holes have been injected into base, then 5 holes were getting recombined with electrons. Why? Because the effective base width was very large. Now, when we have applied more reverse bias at the collector junction, what happens is effective base width has decreased due to the increase in depletion layer. Now, only 3 holes may be recombining with electrons. That means there is a loss of base current. This loss of base current is the gain of a collector current. For that reason, whenever we apply a reverse bias at the collector junction and when we increase it, then what happens is collector current increases. This is called early effect. Now, next coming to common emitter configuration. Now, common emitter configuration is the most important configuration here. Why? Because we make use of common emitter configuration in all our applications as amplifier, etc. Now, let us see the circuit diagram. Here we see that we are having a NPN transistor. Now, in this NPN transistor, the N type emitter has been made common to both input as well as output. Now, the input is taken between emitter and base, and the output is taken between collector and emitter. Now, this is the circuit symbol. You are able to see that this circuit symbol. This is for NPN transistor. Now, here we are having 4 variables: input current, input voltage, output current and output voltage. Here the input current is base current and input voltage is base voltage, whereas the output current is collector current and the output voltage is collector to emitter voltage, like this one. Now, anyhow, the sum of the collector current and base current is always equal to the emitter current. Now, let us see this configuration. This is an experimental arrangement in order to obtain the VI characteristics of the transistor in common emitter configuration. Now, here again you are having a PNP transistor, to which base supply voltage will provide necessary forward bias and collector supply voltage will provide necessary reverse bias, like this one. Now, here now it has been wrongly shown. Now, let us not bother about this one. Now, here this PNP transistor, here we are having 4 variables. I just told you that input current is base current and input voltage is base voltage. Now, we will plot a graph between input current and base voltage for different values of collector to emitter voltage. This will give input characteristics, and if you plot a graph between output current and output voltage for different values of input current, then we will be able to get the output characteristics or transfer characteristics. Now, here you just see that it is the input characteristics. Now, this is a plot between emitter to base voltage and base current. Now, here you can just see that when we make VCB equal to 1 volt and vary base to emitter voltage and note down corresponding base current values, then we will get a curve which is exactly like a PN junction diode. We can see that it is like this one. So, it is nothing but a PN junction diode. Now, here what we have done is we have fixed the output voltage constant to about 1 volt. Now, you can see that it is exactly a PN junction forward biased diode. Now, when we increase the collector to emitter voltage, then what is happening, say for example, we have fixed it to 10 volts, we will get another curve. This is another curve. Now, we just see that this curve also resembles that of a PN junction diode which is forward biased. Now, the shifting of the curves towards right will show that the base current is decreasing. The base current is decreasing for the given VBE values. Now, finally, we are having VC equal to 20 volts. For the 20 volts, after fixing VC is equal to 20 volts, again vary VB and plot IB values, then we will get another curve which is exactly the PN junction forward bias. Now, next coming to output characteristics. Now, here again these output characteristics are of are having 3 states. Now, one is cutoff state, the other one is saturation state, and the rest is active state. So, this cutoff region, active region and saturation region will be for particular values of collector and emitter voltages. Now, I will just show you when we fix the base current equal to 0, that means we are not providing any bias at the input. Then what happens, no base current will be flowing. When no base current will be flowing, then no charge carriers will be injected into the base region, and those charge carriers cannot sweep into collector region. Then the transistor is said to be in the cutoff state. Now, the cutoff state means both the junctions are reverse biased. Emitter base junction is reverse biased and collector base junction is reverse biased. This is shown as a shaded blue shaded region. Now, when we fix the base current to about 1 milliampere, then the transistor emitter junction has been forward biased. When emitter junction has been forward biased, then flow of current starts. When flow of current starts, then what happens, the reverse bias that has been applied at the collector junction will sweep those holes into the collector region, and the collector current also flows. But we have to see that the collector current is also varying with collector voltage. This is due to early effect. What was early effect? The early effect was that whenever we apply reverse bias at the collector junction, and when we increase that reverse bias, what was happening? Depletion layer was extending. Now, due to the fact that base is very thin and it is slightly doped, then what happens, when depletion layer extends into the base region, the effective width of the base decreases. When effective width of the base decreases, then what happens, the base current decreases. but we know that emitter current is equal to base current plus collector current. So, what happens in order to maintain emitter current constant, since the base current has reduced, the collector current increase. So, this there is a small slope, you can see it like this one. That means, for when VCE is almost 1 volt to about VC about 20 volts, you can see that there is sufficient increase in the collector current. That means, here the output voltage is also having some effect on the output current like this one. This is only due to early effect like this one. Now, after that let us fix the base current to about 2 milliamperes. Now, we can see that as the base current increases, the collector current also increases like this one. Now, here we just see that the collector current level has increased. In the same way, make base current equal to 3 milliamperes, 4 milliamperes, 5 milliamperes and so on, and you will be able to see that the curve is shifting upwards, the upward. Now, you can see that any curve is having not zero slope. Zero slope means when VC increases, IC remains constant. Due to early effect, when VC increases, IC also increases. Now, this early effect becomes prominent when base current is more and more like this one. So, you can watch that. Now, here this family of curves is called output characteristics, and this entire region is our active region. Now, coming to another shaded region here. Now, this shaded region represents saturation region. Now, here you just see that a few tens of collector voltage is applied here. Now, this will not be in a position to properly reverse bias the collector junction. For that reason, when collector voltage is increasing, proportionately we are having a collector current increase. Here we just see that. That means, the collector junction is also forward biased. Now, after a few tens of a volts, then the saturation stops, and this entire region is called saturation region. So, output characteristics consists of 3 regions: cutoff region, active region and saturation region. Now, the slope is due to early effect like this. Now, next coming to common collector configuration. Now, common collector configuration is very rarely used for amplification purpose. It can be used as a buffer, that means for impedance matching. Now, let us see that. Now, here you can see that the collector terminal has been made common to both input as well as output. Here the input quantities are base current and base voltage, and the output quantities are emitter current and emitter voltage like this one. Now, this is the circuit symbol. The collector terminal has been made common to both input as well as output. Now, we just see that this circuit is for NPN transistor. Now, here we are having experimental arrangement in order to take VI characteristics of a transistor in a common collector configuration. Here one thing we need to understand. Here we just see that the input voltage is between base and collector. We just see this is base and collector, whereas this is emitter base voltage which forward biases this emitter junction, and this voltage is emitter to collector voltage. Now, once we have fixed this voltage, emitter to base voltage is emitter to collector voltage is constant. Now, when we try to increase V.B.c, we just see that here this voltage we are trying to increase. Now, since this voltage, that is emitter to collector voltage is constant, and if we try to increase this voltage decreases. This voltage is VBE, that is the voltage which is responsible for forward biasing the emitter base junction. For that reason, you can see in the input characteristics that when we try to increase the input voltage means this voltage, base to collector voltage. Now, increase in base to collector voltage will result in decrease in base to emitter voltage, that is forward bias, you can just see that. So, whenever we increase the base to collector voltage, then what is happening, forward bias is reducing and base current is falling. In fact, we just see that the base current is falling. Now, the input characteristics are plotted for two different values of collector to emitter voltage. Now, we just see that the collector to emitter voltage in the first case is 2 volts and in the next case it is 4 volts. Now, it is very unusual. Now, when we compare to other input characteristics, it is a bit different. Now, this difference is attributed to the fact that actually the input voltage is causing the output current to reduce. Now, next coming to the output characteristics of the transistor in the common collector configuration. Now, here we just see that the characteristics are almost similar to the output characteristics of a transistor in a common emitter configuration. Here again we are having same thing, we are having a cutoff region, we are having saturation region and we are having a active region. Now, here we can see that the quantities that are varying are like this one. Now, at the output we are having collector voltage versus emitter voltage, collector voltage versus emitter current, we are having collector voltage versus emitter current, and the plot is exactly like that of common emitter configuration. Now, the plot is between this one. Now, for different values of base current. Now, when base current is fixed to about 0 milliamperes, then almost the transistor is cut off. Now, no emitter current flows, no base current flows and no collector current flows, except for that collector to emitter reverse saturation current which is shown here. This is ICEO, this is the collector to emitter reverse saturation current when the base is open. Now, below this curve the transistor is cut off. Now, when we increase the base current to say 20 milliamperes, now we just see that the curve has shifted up. We just see that the curve has shifted up. Now, again this one we are having a early effect also. The slope is not 0, we are having some inclination. This shows that the emitter current is increasing due to the fact of early effect. Now, in the next curve we are fixing the base current to about 40 milliamperes and next 60 milliamperes and 80 milliamperes and so on. Now, we just see that the characteristics are almost similar to that of common emitter configuration. Now, here we are having a summary of these different configurations. Now, first let us take common base configuration. Now, in common base configuration we are having a high voltage gain, we are having a high voltage. So, wherever high voltage gain is required we employ common base configuration. Now, the current gain is very low. Why? Because in the case of common base configuration, the output current is collector current and the input current is base current, when input current is emitter current. Now, since we know that collector current is always less than emitter current, IC by IE is always less than 1. So, it indicates that no current gain takes place in the common base configuration, whereas in power gain is also low in the case of common base configuration. So, for voltage gain we can employ common base configuration, but we cannot employ it for current gain purpose, and for power gain though it is low we can employ it. Now, in the case of common emitter configuration we just see that the voltage gain is medium. That means, we can employ common emitter configuration for voltage gain purpose, and we can also employ for current gain also. Common emitter configuration can be employed for voltage gain and current gain, and power gain is high bit. Now, but you compare this with common collector configuration. Now, you just see that the voltage gain is very low in the case of a common collector configuration, but in the case of common collector configuration the current gain is very high. It is due to the fact that the input current is base current and the output current is emitter current. Emitter current is even more than collector current. So, this is actually gamma. Beta is the current gain in the case of common emitter configuration, and gamma is the current gain in the case of common collector configuration. Gamma means IE by IB. It is actually 1 plus beta. Now, in the case of power gain it is medium. Common collector configuration is medium, but when we take the case of input and output phase relationship, then we see that there is no phase difference between input and output in the case of common base configuration and common collector configuration. That means, if we apply a positive going pulse at the input, we get a positive going pulse at the output. If we apply a negative going pulse at the input, we get negative going pulse at the output. Whereas, in the case of common emitter configuration, there is a phase difference of 180 degrees. The phase difference 180 degree means, if we apply a positive going pulse at the input, we get a negative going pulse at the output. Now, if we apply a negative going pulse at the input, we get a positive going pulse at the output. Now, regarding input impedance, now the common base configuration is having a low input impedance, whereas common collector configuration is having a high input impedance. This is due to the fact that the emitter base junction is forward bias and it happens to be at the input. Now, this is due to the fact that this is having a collector base junction is the input, and it has been a reverse bias. In the reverse bias, we are having a high input impedance. Now, in the case of common emitter configuration, the input impedance is medium, right. Now, finally, output impedance. Now, output impedance is high in the case of common base configuration. Why? Because at the output we are having reverse bias applied between collector and base. But in the case of current common collector, we are having a low output impedance. In the case of common emitter configuration, we are having a medium output impedance. Now, let us have some live circuit now here you can see that we are having an NPN transistor. Now, this NPN transistor here you can just see that we have applied 0.7 volts at the base. This is the NPN transistor, and you are able to see that the current is flowing in the transistor. Now, what we do is we will make the base voltage varying like this one. Now, we just see that the current has increased enormously. The meaning is that the transistor is going into saturation region. So, if you try to decrease the base voltage, then you can see that almost the current has stopped like this one. That means the transistor has gone into cutoff region. So, now when moderate current is flowing in the transistor, then it is in the active region, and when no current is flowing in the transistor, it is in the cutoff region, and when high current is flowing in the transistor, it is in the saturation region. Now, we can have another circuit also, switching circuit. Now, here you can see that we have applied a voltage between emitter and collector, but despite no current is flowing in the circuit. Why? Because the base has not been biased. Now, here you just see that we are having a voltage at the between emitter and collector, despite that no current is flowing. It is due to the fact that base has not been biased. Now, by simply switching this one, you can just see that the current is flowing in the transistor. That means, we need to provide some base bias, or we need to provide some base current in order to make the transistor conduct. Now, again if we stop or block this base bias, then what happens, the transistor will become cut off. So, that means the transistor is a very versatile device, and in this particular case we are using the transistor as a switch like this one. When switch is on, it conducts; when switch is off, it does not conduct. So, this is regarding the different configurations of the transistor, namely common base configuration, common emitter configuration, common collector configuration, and the respective VI characteristics. So, hope the students you might have enjoyed this session, and hope you might have understood all the nuances of these different configurations and VI characteristics. So, thank you very much.